Hi, I'm Henri Heinonen and my topic today is unconventional computing pushing quantum computing forward. What is unconventional computing? Unconventional computing could be any computing that is not conventional. Conventional computing is usually classical, digital, binary, irreversible, and electrical. Unconventional computing include at least the following: quantum, analog, ternary, decimal, reversible, mechanical, DNA, and optical computing. Unconventional computing could also include FPGAs, ASICs, neuromorphic computing, distributed computing, etc. So what are some of the problems with quantum computing? For example, a large number of physical qubits are required. Imagine a quantum computer with millions of physical qubits with all the required cooling systems and wiring. For example, breaking the Bitcoin would need Grover's algorithm, over 2,000 logical qubits and over 2 million physical qubits, and still it will take 18,000 years to break the SHA-256. Other problems are it is difficult to shed qubits from the environment. It is difficult to make qubits to interact with each other when needed. So those are some of the problems with current quantum computing. So why are we always talking about bits and qubits? Why are we never talking about trits and qubits? One ternary digit, a trit, can represent 1.58 bits. A 21-trit ternary computer could handle 33.18 bits, which is more than a regular 32-bit binary computer could handle. The ternary system uses more transistors, but it should reduce the number of wires to 64%. And there's a good source for that information. Donald Knuth is suggesting an optical classical computer with a ternary logic. With the advent of mass-produced binary components for computers, ternary computers have diminished in significance. However, Donald Knuth argues that they will be brought back into development in the future to take advantage of ternary logic's elegance and efficiency. One possible way this could happen is by combining an optical computer with a ternary logic system. A ternary computer using fiber optics could use dark as 0 and two orthogonal polarizations of light as +1 and -1. Some papers, such as extending the frontier of quantum computers with qubits, are already suggesting that qubits offer a promising path forward. They advocate for a fundamentally different way to perform quantum computation by using tree-level qubits instead of qubits. They substantially reduce the resource requirements of quantum computations by exploiting a third state for temporary variables ancilla in quantum circuits. Past work with qubits has demonstrated only constant factor improvements owing to the binary logarithm of 3 binary to ternary compression factor. They show results in improvements for important algorithms for arithmetic and QRAM. Simulation results under realistic noise models indicate over 90% mean reliability fidelity for their circuit, versus under 30% for the qubit-only baseline. These results suggest that qubits offer a promising path toward extending the frontier of quantum computers. The following is a quote from the Quanta magazine. But the past few years have brought flashes of progress. Engineers have proposed ways to build ternary logical systems even on binary-based hardware, and Cambo, with the support of the US military, has been developing cybersecurity systems that use base tree computing. In papers published in 2018 and 2019, he and his collaborators rigorously described a ternary-based system that could replace the existing public key infrastructure, which includes the digital keys needed to encrypt or decrypt cyber communications. Switching from bits to trits, he said, significantly reduces the error rate, because ternary states better manage erratic information. So what about optical computers? Optical computing is a form of unconventional computing where light waves are used for processing, storage, and communication. An efficient optical computing system should not rely on conversion from photons to electrons because it will make the system slower and bulkier. Optical computing is the use of optical systems to perform numerical computations on one-dimensional or multidimensional data that are generally not images. Optical signals can interact on timescales smaller than a picosecond via an intermediary medium, making high throughputs possible. Optical proof of work. The proof of work of cryptocurrency mining, such as Bitcoin mining, can be tailored to ultra-energy efficient photonic coprocessors. The optical proof of work paradigm should decouple cryptocurrency mining from energy by shifting the operating expenses of electricity to mining hardware's capital expenses. The Opal silicon photonic miner prototype is a modern example of analog computing and optical computing. The high capex and low opex POW mining should also make it possible to make cryptocurrency mining resistant to price fluctuations because it is not expensive to keep that kind of hardware online. So there are also optical qubits. Photonics could work at environments near room temperatures. So that's the good property of photonics for quantum computing, and Xanadu claims they could achieve a fault-tolerant quantum computer with 1 million qubits during the 2020s. So these are quotes from various magazines for analog computing. You don't need zeros and ones to perform computations, and in some cases it's better to avoid them. There are diminishing returns on the digital model, he said, yet it still dominates the industry. If we applied as many people and as much money to the analog domain, I think we could have some kind of analog co-processing happening to accelerate the existing algorithms. Digital computers are very good at scalability. Analog is very good at complex interactions between variables. In the future, we may combine these advantages. I asked him whether the state of analog computing today could be compared to that of quantum computing 25 years ago. Could it follow a similar path of development from fringe consideration to common and well-funded acceptance? It would take a fraction of the time, he said. We have our experimental results. It has proven itself. If there is a group that wants to make it user-friendly, within a year we could have it. And at this point he is willing to provide analog computer boards to interested researchers who can use them with a coarse compiler. Then we have reversible computing. The conventional computing is irreversible, meaning that information is erased and heat is being generated. At room temperature, erasing one bit of information generates about 2.8 zeptojoules of heat. What if computation processes could be reversed in time, making it possible to access the previous states all the way to the input state? Reversible computing could be 100,000 times as cost-effective as irreversible computing in the 2050s. Making gates logically reversible is not enough. The gates must also be physically reversible, meaning the charging and discharging of circuit elements must be adiabatic. It would be interesting to see a similar advancement for reversible computers as with ASIC Bitcoin mining devices in the early to mid-2010s. I have tried to start discussion of the possibility of using reversible computing in Bitcoin mining. The common misconception seems to be that reversible Bitcoin mining would break the SHA-256 algorithm. The reversible version of the algorithm would be different with lots of outputs, and one does not need to share the outputs with the public, so no one could figure out the input. Also, the outputs from the regular SHA-256 do not have enough information to go back to the original input. Memory circuit elements. There are at least 6 circuit elements: capacitor, resistor, inductor, memristor, memcapacitor, and meminductor. And the theory of memristor was proposed by Leon Chua in 1971, and it was finally experimentally observed in 2008. And today it's possible to buy memristors. And here you can see some examples of papers where memory circuit elements are used for neuromorphic computing and also for quantum computing, so they can definitely be useful for to push quantum computing forward, these new memory elements. So the final conclusion is perhaps we should take some notes from other forms of unconventional computing and use those methods in quantum computing in order to push quantum computing forward. For example, maybe we can reduce the number of quantum objects and less wiring and less cryogenic infrastructure in a quantum computer if we use qubits instead of qubits. And maybe we can use those new memory elements that are already used in neuromorphic computing. So thank you for your attention, and you can contact me by sending me some email. Thank you.